Chapter 5, Number 34. A train is traveling up a 2.88 degree incline at a speed of 4.31 meters per second when the last car breaks free and begins to coast without friction. How much time does it take for the last car to come to rest momentarily, and how far did the last car travel before momentarily coming to rest? So what we need to understand here, of course, is that the car continues moving up the hill, but it's being slowed down by gravity. And so it will eventually come to rest and then start rolling back down the other way. But we also have to realize that gravity acts straight downward, and yet the cart has to move along the incline. So let's do a picture just of the last car. We don't really care about the earlier ones. So we'll do something like this, and we'll say that this angle here is the 2.88 degrees. My angle is way too large, but that's okay. And then we have a train car, and the train car is moving with some initial velocity, but eventually comes to rest because there's an acceleration which ends up being entirely down the incline. All right, and then we go off to the side and we say, well, what do our forces look like? So here is the cart, and there are a bunch of forces. There's gravity, which pulls straight down, and there's a normal force, which is the force of the road or the rails against the tires, and that points perpendicular to the incline. And that's going to be the key bit. And then, and this is kind of an unusual trick, but we do it a lot when we have these tilted problems, is instead of taking our usual horizontal and vertical axes to be x and y, we actually pick x to point along the incline and y to be perpendicular to the incline. So neither of them are quite horizontal or quite vertical, although at 2.88 degrees it's not that far off. The reason for doing this is that then we can maximize the number of things that either point along the incline or perpendicular to it, along our axes or perpendicular to them, and then that allows us to say that to minimize how many forces we have to break into pieces. For instance, in this case, we have an acceleration which is along the incline, we have a velocity which is along the incline, and we have a normal force which is perpendicular to the incline, and therefore none of those need to be broken into components. Sadly, we do have the gravitational force, and the gravitational force does not point along my incline. This is just move my axes up here again, along the incline or perpendicular to that, ish. And gravity doesn't do either of those things, so I need to basically find the part of gravity that's along the incline, which I'm going to call FGX, and the part of gravity which is perpendicular to that, which I'm going to call FGY. And I also need to figure out how those relate to the angles I actually have. So I'm going to extend my incline angle, and I'm going to get something like, and I know that this angle here is theta. And then I'm going to go off to the side. I'm going to say, well, what I'd like to do is get some angle in the triangle. I'm going to try and get that angle, which I'm going to call alpha. And that's not trivial to get, but isn't impossible either, because we recognize a third angle, which I'm going to call phi, and we have a right triangle here, which means that theta plus phi must be 90 degrees, because the acute angles of a right triangle have to add to 90 degrees. And then I'm going to say I have a different right angle, not a right triangle, but a different right angle. I have this right angle, because the ground is always perpendicular to gravity, and that tells us that alpha plus phi has to be 90 degrees, because the two parts of two acute angles that make a right angle must sum to 90 degrees. And we can see from those two things together that alpha equals theta. So the net effect of all of that is to say that if I have this thing coming down here, and I have something parallel to the incline, and I have something perpendicular to that, this angle will be the same as the angle of the incline, even though it's no longer pointing in the same way we expect. This allows me to say that FGX over FG, which of course is our opposite side over our hypotenuse, because that's the right angle, that must equal opposite over hypotenuse is always the sine. And so FGX is FG sine theta, and we know that we can always replace the weight with the mass of the object times g. So this component of the weight must be mg sine theta. So why was that useful? Because now we can replace this thing with the following. FGX pointing down the incline and FGY sliding into the incline. And you might say, well, why is that a good thing? Well, because we're going to go back and start looking at things like Newton's second law. To use second law, I want to go to my diagram and I want to say from the free body diagram, the sum of the forces in the x direction, the sum of the forces along my incline is, well, there's actually just the one, FGX, and it points down the incline. So I get a minus sign because it's pointing opposite to my choice of x and y. And of course I would have Fy, and that says that there's a normal force pointing in the direction of y, and there's FGY, but it points opposite as well. And so from the free body diagram, I have that. Then I say, well, but from Newton's second, which is a different statement now, I know that the sum of the forces in the x has to be the mass times the acceleration in the x. And likewise, the sum of the forces in the y has to be the mass times the acceleration in the y. And then from there on in, what I'm going to end up doing is just substituting. I'm going to combine this equation with that equation, and I'm going to say, well, then that means minus FGX has to equal m times minus a. Why the minus a? Because a points down the incline. It points in the negative x direction. And I guess for completeness, I also could have looked at this guy versus that guy, and that tells me that the normal force minus FGY equals m, and there is no acceleration off the incline. This is the idea is that by picking our axes along the incline, we force the other component to be 0, which, as you can see, simplifies our math. But it turns out that this equation doesn't really do us any good anyway, because it has an unknown thing in it that I can't handle. So it's true, but not particularly useful. On the other hand, this equation, very happy for us, because it has a thing we sort of want to get, which is this acceleration. And it's in terms of stuff we can already find. Why do I need that acceleration? Because I want to know how much time does it take to come to rest. So I'm going to bleed off this speed, and I need the acceleration to know how long that's going to take. Right. So to recap, we have minus FGX equals m times minus a, but then FGX was mg sine theta, and this would be minus ma, so the acceleration is just g sine theta. All right, that's the magnitude of the acceleration, is g sine theta. And then we say, oh, well, now we just have kinematics, and we know that the object will obey that Vx, V sub x, will be V initial x plus the acceleration in x times the time it takes to stop, or the time it takes. So when it ends, let's call that TF. When t equals the final time, Vx equals 0. So we end up with 0 equals the initial velocity plus the acceleration, which is minus g sine theta. Why the minus sign? Because again, A points along the incline, but in the backward direction, in the negative x direction. And then we have our TF here. And so now we can solve for TF. We bring this whole thing to the other side by adding plus g sine theta times TF to both sides. And that leaves us with g sine theta TF equals V0, or TF equals V0 over g sine theta, or 4.31 meters per second over 9.81 meters per second square, sine of 2.88 degrees. Our units work out nicely because meters per second over meters per second squared is certainly seconds. And we get 8.74 seconds. To do part B, we have a wealth of information now since we have the time and velocities and the acceleration. I'm going to ignore the time bit though because I happen to like this one better. I'm going to remember that we have an equation that says that V final squared is V initial squared plus twice the acceleration times the change in position. And of course we want it to end at 0, and it has that initial speed, whatever it was, and our acceleration, remember, is still minus g sine theta, and then we would have our final position, whatever we'll call it, like a position L, a distance L up the incline. And then we just solve for L. So we say this is 0 is V0 square minus 2gl sine theta. And then we add 2gl sine theta to both sides, which gives us gl sine theta, 2gl sine theta is V0 squared, and then we divide by everything we don't want. So 2g sine theta. And we're left with L equals V0 squared over 2g sine theta. This is 4.31 meters per second quantity squared over 2 times 9.81 meters per second square, which is the free fall constant, times sine of 2.88 degrees, and all told that becomes 18.8 meters, which is how far it goes up the incline. And we're complete. I'm just going to solve this problem again from the other viewpoint, just to say that it doesn't really matter which way you go. The other route is to say, oh, it's constant acceleration motion. So we can say that the place you end up is where you start plus your initial velocity times the time plus 1/2 times the acceleration times the time squared. So for us, we start at 0, and then it's moving up at 4.31 meters per second, and the time was 8.74 seconds. And then we have 1/2 times minus 9.81 meters per second square times sine of 2.88 degrees times 8.74 seconds squared. And if you throw all of that into a calculator, you get 18.8 meters, just like before. And so either way would have worked fine.